Hello there, this is a geometry video. It is chapter 10, section 3, and today we're going to be discussing arcs and chords. Now before you get too excited, we're not talking about music chords like the ones you would use to play the guitar and such, although that's pretty fun too. We're talking about geometric chords in a circle. So, a chord is a segment that has endpoints on a circle, which we already knew from before. If a chord, however, is not a diameter, then its endpoints divide the circle into a major arc and a minor arc. So here we have a diagram, and we have a chord FG and chord JH. So basically what it's saying is that if the chord is not a diameter, which it's not a diameter if it doesn't go through the center, and this is not going through the center, then that means that this chord FG separates or divides the circle into a major and a minor arc. So the major arc would be going from here all the way down here, or a minor arc which would be F to G. Likewise, JH would be a minor arc here, or a major arc that direction. So we have our first theorem for this section, which is theorem 10.2, and it says in the same circle, or if you have congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. And one thing that I want to stress right now before we go any further, because you're going to see this phrase a lot in this section, is the if and only if that we discussed a while back. And the cool thing about if and only if is that it means that this theorem can be stated in both directions. In other words, the conditional and its converse. So that's saying that two minor arcs are congruent, then their corresponding chords are congruent. Or you could think of it as if their corresponding chords are congruent, then the two minor arcs are congruent. It can go both directions. So in our example, it says here that arc FG is congruent to arc HJ. So here's FG, HJ, and because that's the case, then FG, the length of FG is the same as the length of HJ. So that being said, we're going to do our first example here. It says in the embroidery hoop, which is down here, segment AB, which is a chord AB is congruent to chord CD, and the measurement of arc AB, which is right here, the arc, is 60 degrees, and they want us to find the measurement of arc CD. And since we know already that AB is congruent to CD, then the measurement of arc CD should equal the measurement of arc AB, which we know is 60. So the measurement of arc CD is also 60. And so just like that, you get your answer for your first example. So you can do it yourself, number one, also referring to the same diagram. And then we'll go on to our next item. In example 2, it says in the figures circle J, which is right over here, circle J and circle K are congruent circles, and furthermore arc MN, which is the arc part here, is congruent to arc PQ, and they want us to find the length of PQ. So like we said before, you can go with the theorem both directions. So in this case, because we know that the arcs are congruent, then the chords must be congruent. So that means that PQ is going to equal chord MN. And since our diagram is says that PQ is 3x minus 7, we replace PQ with 3x minus 7, and then in MN it's 2x plus 1, so we'll substitute that. Then we just do some simple algebra, subtract 2x from both sides, bring the 7 to the other side, and we'll get 3x minus 2x is 1x, negative 7 plus 7 is 0, and over here 7 plus 1 is 8. So x equals 8, but notice they didn't ask us to find x, they said find PQ. So once we know that x is 8, we want to take our PQ, and it's 3x minus 7, so we want to go 3 times 8 minus 7, which is going to be 24 minus 7, and so at the end of the day, PQ is going to equal 17. PQ equals 17. And that's how you do example 2. So at this point you can do it yourself number 2 in much the same way. And then we will move on to our, oops, I didn't mean to do that. I meant to erase that. Now I've saved it for no apparent reason, but that's okay. Our next theorem is theorem 10.3. And as I mentioned earlier, you'll notice that it says here, if a diameter or radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. And so basically what you have here is, instead of the if and only if lingo, you've got the theorem and basically its converse here. Here we're saying that if the diameter of a circle is perpendicular to the chord, then it bisects the chord and its arc. Over here we're saying that if it's a perpendicular bisector of the chord, then it's going to be the diameter of the circle. So they're basically converses of each other here. But just to explain what's going on here, you have the diameter, which is AB, and that happens to be perpendicular to the chord XY. And so if that happens, then what we know is that the diameter, AB, bisects the chord. So then this piece here, X to Z, is going to be equivalent or congruent to the piece Z to Y, which is what you see here. It says XZ is congruent to ZY, and XB is congruent to BY. Now this is an arc symbol versus a chord or a segment symbol, okay? Remember that a chord is a segment. So the diameter, if it's perpendicular to the chord, is going to bisect the chord itself and also bisect its arc. So that's what it's talking about, the XB to BY part. And then over here in the converse, if you are the perpendicular bisector, which in this diagram it's indicating that it is, and we know that because you see the perpendicular symbol, but you also see the tick mark here that's indicating that this segment is the same as this segment, so that therefore it bisects, and therefore it's the perpendicular bisector. And if you're the perpendicular bisector, then you must be the diameter or the radius of the circle. So AB being the diameter, or the radius would be BC. So that being said, we're going to use that and apply that into example 3. And then for example 3, we're going to be focusing on circle S, which is down here. So make sure you're looking at this example, not the ones up here, but this guy right here, that diagram. It says the measurement of arc PQR, which is this arc here that's associated with the chord PR, is 98 degrees. And they want us to find the measurement of arc PQ. Alrighty, arc PQ. So, what we know is that if the diameter or the radius is perpendicular to the chord, which in this case, the radius here is perpendicular to the chord because of this symbol there, then it's going to bisect the chord and its arc. So basically what we know is that it's going to have to cut the arc PQR in half. So the measurement, keep doing that. It's not fun. So let's see here. The measurement of arc PQ is going to equal half of the measurement of arc PQR because it's perpendicular to the chord. And so since we know that the measurement of arc PQR is 98, we can furthermore say that it's 1/2 98, which equals 49. 49 units. So in example 3, the measurement of arc PQ is equal to 49. So now you can do it yourself number 3, and then we will go on to our next item of business, which is example 4. Example 4 is going to require a little bit more work, but it's not too difficult as long as you're looking at the diagram correctly. Alrighty, so here we go. In example 4, it says, in the stained glass window, diameter GH is 30 inches long. So here we have G to H, and that's 30 units long. And then chord KM is right here, chord KM, and that's 22 inches long. And they want us to find JL. JL goes from the center of the circle to where the diameter and the chord intersect. But notice that it's not the entire radius. That would have been easy to figure out. It's not the entire radius, it's just the portion from the center to right where the diameter and chord intersect. So the easiest thing for us to do is to kind of generate a triangle out of this guy. I'm not sure if you guys can see that there's a symbol here that says it's perpendicular, but what I want to do is kind of draw ourselves a little bit of a diagram so we can see a little bit better what's going on. And this point is going to correspond with the center of the circle, which is J. And since this point is L, which is where it meets with the chord at a 90-degree angle, so this point here will be L. And then K is the point on the circle. So basically, if I were to take this triangle, what I'm drawing for you over there is J, L, K, like that, okay? And what I want you to notice is that the distance from J to K is a radius of the circle. And since we know the diameter is 30, then that means that the radius would be half of that, or in this case, 15. So I'm going to go ahead and put 15 on my diagram. And then furthermore, we are told that KM is 22 inches long, and KM is this chord here, but it is perpendicular to the diameter, which means that it bisects. So that means that if KM is 22, then KL would be half of 22, which would be 11. And so just like that, we have two parts of the triangle, and what we're trying to find is JL, which is this missing piece here, but we can use Pythagorean theorem to get that portion of the triangle. So we're going to go ahead and do that, and so you're going to get JL squared, that's the first leg, plus 11 squared is going to equal 15 squared. So JL squared will equal 15 squared minus 11, so we're going to take the 11 squared to the other side. To get rid of the square, we're going to square root. So JL is equal to the square root of 15 squared minus 11 squared, which just so happens to be 104. So the exact answer is the square root of 104, but they are going to allow us to approximate this. So the square root of 104 is approximately 10.20, and it was in inches. They had told us it was 30 inches long, so our dimensions are in inches, our units are in inches, and that is how we get JL. Alrighty, so in a similar way, not the exact same way, but in a similar way, you're going to need to create a triangle over here to try to find TV. Now remember that TV is the entire chord, but we know that since it's perpendicular to the radius, that the chord is bisected in half. So we know that the radius is 6 and 5 combined, because this section is 6 and this is 5. If you add them together, you get 11 for your radius. And if you were to complete this circle and have a right triangle like this, the hypotenuse would be 11, this leg would be 6, and what you would be looking for is S to V. And if you could figure out what S to V is, then you could double it to get TV. So I've given you some hints on how you can do it-yourself number 4, much like example 4. And so now I'll leave you to it, and then we will go on to our last theorem. Here we go at 10.5. Oops, I'm so sorry. I didn't mean to close that one. Do not copy what's on the board right now. That is not part of your lesson. And let me bring that do-it-yourself 5 back. Sorry about that. But here we have our final theorem. And again, we have a diagram to kind of help us illustrate the theorem. It says in the same circle, or if you have congruent circles, two chords are congruent. And here's that phrase again, if and only if. That means you can go both directions. If and only if they are equidistant from the center. So the chord FG is congruent to the chord JH if and only if the distance from L to Y is the same as the distance from L to X. And that distance has to be a perpendicular distance, just in case that wasn't clear. So that's our theorem, and we're going to use that theorem in example 5. It says in circle A, WX equals XY, which equals 22. So if you look at the diagram, WX equals XY. WX is a chord, and XY is a chord, and they're both 22 inches or 22 units long. So because of that, we've met the criteria that two chords are congruent. But that's only the case if they're also equidistant from the center. So here you can see marked that the distance from the center to the chord at this 90-degree angle is 5x here, and this distance to the other chord is 3x plus 4. So the only way for these to work is for them to be equated to each other. So what we know is that in example 5, we've got that AB has to equal AC. All right, so we know that since the chords are congruent, then the distance from the center has to be congruent. So AB has to equal AC. And since AB in the diagram is marked as 5x, we're just going to substitute 5x. And since AC is 3x plus 4, we're going to go ahead and substitute that guy. And then we're just going to do some faithful little algebra here. And 5x minus 3x is going to give you 2x equal to 4. And if you divide both sides by 2, then we're going to get that x equals 2. But again, they're not asking us to find x. They're asking us to find the length of AB. And since AB is equal to 5x and x is 2, then that means that AB is 10 units long. And there we go. So now in do example number 5, you will finish that example, and when you have completed that do-it-yourself question, you will have completed your notes for this lesson, and I will see you in class. And thank you for watching.